Hello, everyone. My name is Richard Ren. I'm a PhD candidate at Carnegie Mellon University. Thanks for your interest in my research. Today, I'm going to present my work on multi-objective multi-agent pathfinding. Multi-agent pathfinding, or MOPF for short, aims to plan collision-free paths for a set of agents from their respective start and goal locations while optimizing a single objective, such as path length. However, in many real-world applications, such as disaster handling, logistics, etc., multiple conflicting objectives may need to be optimized simultaneously, and those objectives are hard to be combined as a single objective. For example, we want to minimize path length, travel risks, and task completion time, etc. To solve this problem, in this work, we consider a multi-objective, multi-agent pathfinding problem, or MOMAPF for short. So in this problem, we have a set of agents represented by an index set I, ranging from 1 to n. All agents move in a workspace represented as a graph. For each edge in the graph, a non-negative cost vector of length m is associated. For example, on the right, every edge in this graph is associated with a cost vector of length 2. Each component in the cost vector corresponds to an objective to be minimized. Besides, we define an individual path to be a sequence of nodes, and a joint path is a set of individual paths for all agents. It takes an agent one time unit to move from one node to another. A conflict between agents is either a node conflict or an edge conflict. For a node conflict, IJVT, it means that agent I and J locates at node V at the same time t, and therefore there is a collision. For an edge conflict, IJET, it means that agent I and J are trying to go through the same edge from the opposite directions at the same time t. And in this work, we use /C to denote a conflict checking function over some joint path. The cost of a joint path is the sum of cost vectors of all edges presenting the path. For example, on the right in plot 2, the red robot has a path of cost 12,2, and in plot 3, the yellow robot has a path of cost 7,7. The joint path of both red and yellow robot is 19,9, which is the sum of 12,2 and 7,7. Now, to compare two paths, we compare the cost vectors related to them. Specifically, given two cost vectors A and B, if every component in A is less than or equal to the corresponding component in B, and there exists at least one component in A such that it is strictly less than the corresponding component in B, we say that A dominates B. If A does not dominate B, or B does not dominate A, then both A and B are non-dominated to each other. And among all paths connecting the start and the goal, the subset of paths with non-dominated cost vector is called the Pareto optimal set. For example, in figure 4, the red robot itself has two individual Pareto optimal paths with cost vector 12,2 and 7,7. Clearly, neither of them dominates the other. And finally, in this MOMAPF problem, the goal is to find all conflict-free, cost-unique Pareto optimal joint path for all agents. So to solve this problem, one related approach is conflict-based search, which solves multi-agent pathfinding problem, but optimizes only a single objective. On the other hand, multi-objective graph search algorithms, such as NAMO-A*, solves a multi-objective but single-agent path planning problem. Our approach, multi-objective conflict-based search, or MOCBS for short, leverages both of them. It is a two-level search algorithm with both a high-level search and a low-level search. MOCBS initializes by using a single-agent multi-objective planner, such as NAMO-A*, to compute all individual Pareto optimal paths, ignoring any other agents, and then takes the combination to get an initial set of join paths. For each of those join paths, a high-level search node, which contains the join path, the cost vector of this join path, and an empty constraint set is generated. Those generated high-level search nodes are then inserted into open, a list of high-level search nodes, for further expansion. And then for each search iteration, a node with a non-dominated cost vector in open is popped and expanded. And by expansion, we mean we check for conflict at first. If a conflict is detected, MOCBS splits over this conflict by generating two constraints. One constraint forbids agent I from entering node V at time t, and the other constraint forbids agent J from entering node V at time t. For each generated constraint, MOCBS invokes the low-level planner to compute all individual Pareto optimal paths subject to the generated constraint for that agent. Here, the low-level planner is a constrained single-agent multi-objective planner. And after the low-level search, for each computed individual Pareto optimal path, a new high-level node is generated and inserted into open for further expansion. When no conflict is detected during the expansion, a conflict-free join path is found. The cost vector of this join path, GK, is used to filter open lists, which removes all candidate nodes in open with a dominated cost vector. Those nodes can be removed because they cannot lead to a Pareto optimal solution. MOCBS terminates when open becomes empty, which guarantees that all Pareto optimal solutions are found. Okay, one bottleneck of MOCBS is that at initialization, the number of routes can be huge. Consider a case with 10 agents, and each agent has 10 Pareto optimal paths. In this case, there are 10 to the 10 root nodes to be generated, which is astronomical. And to overcome this challenge, we propose a variant of MOCBS called MOCBS-T, where T stands for tree-by-tree expansion. As its name suggests, MOCBS-T exhaustively searches over one route, which represents a search tree, before search over the next tree. By doing so, MOCBS-T can defer the generation of routes until absolutely needed. Additionally, MOCBS-T can also find the first feasible solution as quick as possible by exhaustively searching over a single tree. Okay, to test our algorithm, we use maps from an online benchmark set for MAPF with cost vectors of edges randomly generated between 1 and 10. We use NAMO A* to search over the joint configuration space of agents as a baseline approach and compared it with our proposed MOCBS approach. The runtime limit for each tested instance is 5 minutes. Here, we fixed the number of agents and changed the number of objectives from 1 to 4. So in this test, we use an empty world of 16 by 16 size. On the left, with 2 agents, MOCBS performs worse than the baseline in terms of success rates. On the right, with 4 agents, MOCBS clearly outperforms NAMO A* in terms of both success rates and average runtime over solved instances. It is also worthwhile to point out that when the number of objectives increases from 1 to 4, the number of Pareto optimal solutions increases from 1 to over 100, which indicates the difficulty of MAPF problem. In addition, we also compared MOCBS-T with MOCBS in 3 different maps from the benchmark set. This time, we fixed the number of objectives at 2 and changed the number of agents from 2 to 10 with a step size of 2. From the results, we can see that MOCBS-T has a similar success rate to MOCBS about finding all Pareto optimal solutions. In addition, MOCBS-T has better success rates than MOCBS about finding at least one solution within the time bound. However, both algorithms do not scale well with respect to the number of agents. So to conclude, in this work, we introduce a multi-objective, multi-agent pathfinding problem. To solve the problem, we propose MOCBS and MOCBS-T to solve it. We also verify the proposed algorithm with numerical results. For future work, one can consider improving the scalability by investigating whether existing CBS improvement techniques are still applicable to multi-objective CBS. One can also consider a suboptimal version of MOCBS to approximate the Pareto-optimal set with property guarantees. And finally, one can also explore how to leverage other MAPF planners such as MSTAR, EPE, A-STAR to solve MOMAPF. Okay, so this is the end of my presentation, and thanks for your participation.